This is a more difficult centripetal motion problem than the one for which I did an earlier video, and just to give you sort of a variety of how complex it can get. So we have an overhead view of a car going around the circular track as usual with some radius of curvature of r. It is banked at some angle theta, and so if we're dealing with a frictioned situation, so the static coefficient is greater than 0, what's the maximum angle theta so that the car can take the track at a speed v and not slip? So normally it's like this at some particular angle, and as we increase it, at some point the car is going to start to slip down the track. So if the car did slip, as the angle increases, the car slipped towards the inside of the track, which is what I just said. Therefore, the friction acts up the track. We're going to go through the process now that I've done in so many other videos. So we start out with the force diagram of the car. We have weight going down, normal force perpendicular to the track, and friction acting up the track. The direction of acceleration is horizontally to the left, given the way I've drawn it, and that's because the acceleration is towards the middle of the circle. I'm going to establish my coordinate system like this. And so we're just working through force diagram, acceleration, coordinate axis, then decomposition. I have to break up the normal force and the friction. And there are a couple of ways of looking at it, but if you look at the earlier video, we have y sine theta towards the middle of the track, y cosine theta acting up. And because friction is perpendicular to the normal force, that the trig functions switch. And so the horizontal for normal was sine, the horizontal for friction is cosine, and then vertical, one's cosine, one's sine. The equations of motion will have two, because I have one object in two directions here. So y sine theta minus fs cosine theta is equal to mass times the centripetal acceleration, and then y cosine theta plus fs sine theta minus the weight is equal to 0 because it's not accelerating vertically. We do substitution in y sine theta minus mu s y cosine theta, so that's the formula for maximum friction since we're looking for an extreme here. That's the formula for static friction. That's the formula for centripetal acceleration. And we have friction right there also. And then weight. So now it's left to solve. I'm going to solve this two different ways. So first thing so one of them is more difficult than the other. I'm going to start out with the more difficult one. So I factor normal force out of the two previous equations. And then I do division here to get rid of my normal forces. And so I'm left with basically this divided by that is equal to this divided by that. The masses cancel out. I'm left with v squared over gr. Now, if you look at the previous video, this is just a quick check. If mu is equal to 0, like it was in the frictionless situation, we end up with the speed being the square root of gr tan theta, which is what we got in the previous video as stated there. I'm also going to let a equal v squared over gr, just because the more I write, the more chances I have to make a mistake. And so I'm just going to simplify what I've written here. So I have, using a for this part, I'm just going to write mu for mu sub s, s for sine, and c for cosine. And so we end up with this equation right here is simplified down into this, given my 4 definitions there. It's a matter of just going through the math. So multiplying both sides by cosine plus mu sub s, and then distributing, I am ultimately solving for an angle here. So I need, right now I have my angle theta sort of captured by sine and cosine, and so I need to get in terms of a single trig function, and so I get all the cosine terms on one side, sine terms on the other, and it gets me here. Factor out sine and cosine, square both sides, and so I'm left with a plus mu squared, and then I get cosine squared, and one of the basic trig identities, that sine squared plus cosine squared equals 1, therefore c squared equals 1 minus s squared, and so I make that substitution there. Distribute, or partially FOIL, however you want to look at it. Anyway, multiply the 1 times this, and then negative s squared times that. So now I have a sine squared term here and a sine squared term here. I add this to both sides, and that's equal to what's ever left over, so that is what's left over. I then factor out sine squared, and I'm left with this. And since I'm solving, I now have in terms of a single trig function, I divide by this, and ultimately comes down to that. So I have a value now for sine squared. So sine squared is equal to that, which is written on the other page. This bit right here happens to factor relatively nicely. I've rearranged the order of the denominator just a little bit, just to give a quick contrast. This is the way it was written on the previous page, and I just changed the order around a little bit so that it looks easier to factor. So I have a 1 plus a squared here, and when I factor out mu squared plus mu squared a squared from here, I'm left with another 1 plus a squared, in which I then can factor that. So now s is equal to the plus or minus the square root of all that, and so theta is equal to the arcsine of plus or minus that. And so now I have a formula for the angle, and so let's just stick some numbers in. So traveling about 65 miles an hour, assume that we're somewhere on a planet like Earth, radius of curvature is 100 meters, and mu sub s, which is roughly right for asphalt and rubber. So that gives me an a value, capital A value of this, which reduces down to 45/49, or you can do it as a decimal. And so now plugging into this equation over here, so theta is equal to the arcsine of plus or minus the square root of that, and you just start working, use a calculator. We get two different angles here. This is the one that makes sense. The other angle, as indicated in the drawing right here, means that the track has sort of dipped over, and that's because mathematically there are two solutions to solve this. However, physically only one makes sense, and so it's 81.22 degrees. Now I want to solve it using a second technique. So technique number 2, I'm going to start with where we were on the page 2 of this, and so they could exploit the idea, the fact that tangent is sine divided by cosine, and I'm just going to let capital T equal tangent of theta. And so I multiply top and bottom by 1 over cosine, and so I get sine over cosine, which is tangent. These when I distribute to the second one, the cosine cancels out. Over here, cosine cancels out, left with a 1, and I get sine over cosine. I immediately have only one trig function, and so I do a little cross multiplying, or multiply both sides by this denominator to get this. So I have t minus mu is equal to 1 plus mu t quantity times a. Distribute the a. Ultimately, I'm looking for the angle. I get my tangent terms on one side, so I bring this over to here, and I bring this over to there, and I'm left with t minus a mu t is equal to a plus mu. T times 1 minus a mu is equal to a plus mu, and so divide by this since we want tangent by itself, and ultimately theta is equal to the arctan of that ratio. Much simpler looking ratio, and we end up with, again, one answer. Now, mathematically, there would be a second answer in the third quadrant, and that means that if theta is defined from here, it's basically down like that, which in the car is here. And that just doesn't make any physical sense. But 81.22 degrees. If instead I wanted to go for the minimum angle instead of the maximum angle, the difference is that as the angle gets smaller, the car is more likely to go slipping off towards the outside. And so friction switches directions. And so in contrast, this is the set of equations when we're looking for the maximum angle, and then looking for the minimum angle, the sign of friction changes, because basically it flipped 180 degrees, so of course friction flips signs. And so similar technique that we go through. I'm going to just stick with technique number 2, make the substitution for friction. We factor y out, so technically there's a y here. And then when we divide, the normal force cancels out. We multiply top and bottom by cosine to get this. And then ultimately we want to get tangent by itself. We end up with theta being 3.904 degrees. And there we go.